Good morning, I'm playing with junk again. And as usual, it's not really junk, it's in fact a brand new power supply. But it is one of the kind we don't really need. We also have 4 of them, and well, it's a great opportunity to look inside because there are a couple of special things about this. Now, the power supply itself is not really big. So here, for example, is a picoculk to compare. I think, well, it's a little bit narrower, a little bit higher, a little bit longer, but all in all, it's probably about the same volume. Okay, a small power supply. How about a little game? You may guess how much power this thing has. I don't know, 500 watts, 1000 watts, 2000 watts. Okay, I tell you, it's 3200 watts. And I'm also pretty sure you have never seen a connector like this, except you're working in a data center, because that's a special data center type power supply for a Dell R770 server. That's the 17th generation of Dell server, the newest at the moment. And if you look at the specs, you see it's made for 277 volt AC or 336 volts DC. So you have an AC or DC power supply, and well, the voltages are pretty unusual. So what is it good for? Here is a document from Dell about power supplies in data centers. And you see they use now 3-phase 277 or 480 volts. 277 is from each phase to ground or to neutral, and 480 volts is from each phase to any other phase. On the last page of the document there's a pretty interesting table. It's about the efficiency of power supplies, and as you can see, the best efficiency of 96% is when the power supply is only delivering 50% of its maximum power. At 100% the efficiency drops to 91.5%. and similar values are below 50%. So if you want to operate your server as efficiently as possible, well, you take a 3200 watt power supply and operate it at about 1600 watt, so then you get this 69% of efficiency. Okay then, how Dave Jones always says, don't turn it on, take it apart. And the reason why I do not turn it on is because I don't have a 277 volt power supply here. I could go to 250 volts with my Variac, but well, it's not really interesting to turn a power supply on. Okay, okay, it's already open. What do we have? We have a giant capacitor here. Maybe because it's a DC power supply, so you have to, I don't know, they provide a little bit more power outage resilience. Although in a data center that shouldn't be necessary. Well, on the other side it's a 3200 watt power supply, so I assume it is necessary to have a relatively big capacitor. There are two more screws here. So, did I miss any screws? Probably that one. Yes. It's always a good trick to look at the bottom, then you see where the screws are out and where not. Yeah, that's the grounding screw with the split spring washer here. Okay, so we have that. By the way, the power supply costs about $1,500 when it's new. So that's already a value where most people would buy an entire PC for that money. Okay. Yeah, I think if I want to take it further apart, I need a soldering iron. I will probably do that. There's a lot of insulation stuff here. Ooh, quite a big chip for a power supply. Wait a minute. Oh, okay, yeah. I have to show you that up close. Well, that's something I haven't seen before. You probably know these small connectors here. They are usually in phones or other electronic devices. This one is a type with 4 contacts, so you usually have a flat ribbon cable that goes around to another place. But here they're using it to connect this ground plane here. So you see there's only one piece of copper, and that piece of copper goes all around here. It is insulated with this, well, probably mylar or whatever that is, and that's just the shielding for this microprocessor here. And normally when they do shielding, by the way, there is another connector that was connected to that shield here. And normally they just solder these shields to the PCB. They don't use a connector. I don't know why they choose to do that. So that's probably their approach to a high-end power supply. I don't know. Maybe they don't trust the manufacturer to properly solder that shield to the PCB. I don't know. But interesting choice. You also see that the microprocessor here, oh, by the way, what is it? It's an F28039 CSP set, I don't know, from Texas Instruments. The microprocessor is mounted on a separate PCB, so the whole PCB is then soldered to the main PCB, the same for this little guy here. Again, I don't know why they are doing this. Normally, well, it's not unusual to have a microprocessor in a server power supply. It handles everything, power distribution, serial number. There is also firmware for the power supply to make it run properly with all the other hardware. But normally they are mounted to the main PCB directly. Don't know why they did this, but there are many don't knows in this power supply. For example, these heat sinks here are interesting. You can see there is a large, I don't know, chip. Let's just call it a chip, and on the rear side of the power supply we have these heat sinks. But then we also have these little guys here. They look like some metal blocks, and I think that's exactly what they are, because I'm pretty sure that's some sort of heat sink. Again, you can see there's a whole row here, and also on the other side. I mean, if you solder a piece of metal to the PCB, that automatically acts as a heat sink. And of course we had a ventilator, a fan here, which is now here, and that blows air lengthwise to this power supply. And yeah, a little bit more heatsink, why not? I also saw power supplies that had soldered on heatsinks here, where the connector is, to cool down the connector surface here. This one doesn't have that. Maybe they used a little bit better connector to keep the temperatures down. I mean, we are talking about, how much is the output? 12 volt and 262 amps. Yeah, that's about 3000 something watts. 262 amps. That's more than your car will need to start. That's normally about 100 amps or so. So you could start 2 cars simultaneously with one of these power supplies, if you have the right input voltage. Okay, let's crack it apart a little bit more. Alright, we can see there is a fuse. It's a standard glass fuse in a heat shrink tube on a separate PCB. I don't know why they didn't just install the fuse directly on the board and going with this PCB here, because I don't see anything on the PCB except this wire here that was connected to that point. And where is that point going? Oh, looks like ground. Maybe not. Okay. 400 degree, a little bit hotter than normal, and it comes out. And as I said, there is absolutely nothing except that wire here. I mean, even the PCB has about the size of the fuse. I mean, they just could have placed it like that, but they didn't, for a reason. We just don't know the reason. There's always a reason for everything. Okay, then we have some input mains filter stuff. And what I'm missing is the main rectifier. And I think that's the board here. Let's take that out. Well, that's the reason why it is so complicated or so difficult to repair these things. All the copper traces are massive. You need a lot of heat to even unsolder anything. And I think in this case I will go the brutal way and just break it off. And of course what I missed is this little connector here, which was actually not soldered to the PCB, but okay, I didn't need to desolder that. So what do we have here? The big boys here are MOSFETs, IMT65R026. They are made for 650 volts and 81 amps continuous, or 217 amps peak. And the reason why they have so many pins is simple. You can't just let 217 amps to one pin. That would melt, that would blow up in flames. So pin 3 to 7 are the source pin. They are all in parallel, and then pin 1 and 2 is gate and some sort of gate driver. I don't know what that means. You can look up in the data sheet if you want. The smaller chips here are also MOSFETs, 650 volts and 41 amps or 151 amps peak. Yeah, there are just the smaller version of the big ones, and there are 4 on this side and 4 on the other side, so I assume that's the rectifier for the input voltage, a controlled rectifier that has the advantage of having lower losses than just for diodes. And here is the gate driver chip. It's a 2-channel gate driver that drives all the MOSFETs here on this PCB. And it gets its signal from the microprocessor down on the main PCB. And now let's try to take out this output coil board here. I thought it was a transformer, but I think now it's just an output inductor, because left and right of that inductor you see these MOSFETs that act as rectifier diodes. And instead of having large capacitors at the output, they took a large inductor that serves the same purpose. It smoothens out the DC voltage and gets rid of all the ripples. So I think that's it on this PCB here. You see, I tried to unsolder it, but that was not very successful, so I had to go a little bit more brutal with larger pliers. But it seems even this is not enough, but finally we get it out, and that's the main purpose of this video here. Okay, I'm back from the datasheet. It's pretty amazing. It's a ISCH42N04, LM7. It's a MOSFET, each of these, with a maximum voltage of 40 volts. That's okay, because we are generating 12 volts. And a continuous power, continuous current of 541 amps each one. 540 amps for each of these is possible. I think they are a little bit underpowered here. By the way, the peak amps is 2164 for such a little device. That's something that blows my mind. How do you put 2000 amps to a little device like that? So this will never happen in this circuit, of course, because I think then you need a little bit more of cooling, because the only cooling here is the airflow and the PCB traces themselves. And of course this 2000 amps, that's only for a very short period. You only can generate a couple of joules with that. By the way, the maximum power dissipation is 234 watts per MOSFET here. So again, that certainly won't happen in this circuit, because if you generate 230 watts in one of these little chips here, yes, it would simply blow up, go up in flames and smoke and everything. Yes, but that's a pretty capable board here. Of course, they use these MOSFETs as controlled rectifiers, and I think we see now why we need such a large microprocessor to, well, control everything, because it's all about efficiency. You could do the same with normal diodes, of course, but then you will never get the 94% efficiency here. Well, let's take care about this thick PCB here. Yeah, the dismounting method is pretty simple. In fact, it probably wouldn't be necessary to do that. At least here we have a connector, but the other side was soldered, so I still don't understand what the philosophy here is. You have connectors, you have no connectors sometimes. Yeah, look at it. We have a ferrite core that seems to go through the PCB here. There are some slots here. Yeah, you can see that. And they're using the PCB as the winding for the transformer, or for this coil, or, well, let's break it open. Hopefully, oops, without poking a hole into my finger. Well, that worked pretty easy. Come on. Yep. Oh, okay. That was too easy. So, yeah, we can see that there is one winding here going one time around, so it's one turn. And here we have another turn in the same fashion here. Yeah, I think that is not much a power transformer, maybe a signal transformer of some sorts. Although even with one winding, if you choose a high enough frequency, you can transfer quite some power. So I consulted a few more data sheets, and I didn't find anything for that, because I'm just guessing what it is, but it has more labels and pictograms than the end credits of a Hollywood movie. So it's something that is safety related. I also see a 250 volt AC symbol there. And I think from measuring with my multimeter, it's actually capacitor. Well, a high-end safety mains capacitor, something like that. If you know better, let me know in the comments. Then we also have an interesting chip here. It's the NV6115 from Navitas. Never heard of that company before. And it seems it is a MOSFET driver, which makes sense, although we don't have many MOSFETs. We have one MOSFET here. That's probably a MOSFET 2. Yes, it's also directly connected to that chip. And the interesting part about that chip, it can switch up to 2 megahertz. So that explains probably why we only have this one winding transformer here, because the higher the frequency, the smaller the transformer can get. And at, let's say, 2 megahertz, you can transfer quite a lot of power with only one winding. It's more like a high frequency antenna transmission here than an actual transformer, but yeah, high frequency, small components. Alright, let's address the elephant in the room. What is this giant capacitors? It looks like it's 2 capacitors, but I don't think so. Oh, let me get the right tool. And that's a sharp knife. It seems they didn't trust the original heat shrink tube around the capacitor, so they added this yellow insulator here. Okay, there are 2 soldering points here. Maybe I'm able to get that out without destroying. Alright, that's it. Only 2 pins, but pretty large ones. Okay, let's see what we have. 1300 microfarad at 475 volts. So I definitively wouldn't like to hold that in my hands when it's fully charged, because, well, it's a little bit difficult to kill you, because you had to touch these 2 pins here with both hands. But it could probably burn quite a hole in your skin. And either way, that's a bad thing to experience. Yeah, it's just one large capacitor. I think I will keep that because, yeah, could be nice for some high voltage Big Bang experiments. Okay. We have another set of large switches. Are those the same as before? 65R04. No, it's a little bit a different type, but I'm pretty sure it's 4 big MOSFETs here for some probably rectifying or switching. Well, we also need a primary or a secondary switcher that turns the incoming AC or DC into high frequency AC, so we can use those small little transformers. That's probably that. Then here we have most likely drivers for this, for the MOSFETs here. And then we have these metal bumps here, these little cubes. And as I said, they are probably just heat sinks. You can see there are places for more of these heat sinks, but they are not populated. Let me take one out here and see what it actually is. Yeah. That's exactly what I thought. The question is, it looks like copper here on that side, but that could also be the copper of the PCB. Let me see. Copper would make sense because it's easy to solder. Aluminium is not so easy to solder. Yep. Yeah, it's clear. It's definitively, come on, focus. I don't know if you can see the color, but I can tell you this is copper. Maybe not. Okay, we have little copper cubes as heat sinks. And of course the same on the back side, directly underneath. So that's, well, thermal improvement of the PCB by adding some copper chunks here. Alright, I googled a little bit the data sheets of the two large processors here. And it turns out there are Texas Instruments TMS 320 series. That's the F280039. And the larger of the two, it's a real-time microcontroller with a 32-bit DSP core. It has a floating point unit. It has a trigonometric math unit. It has 384K of flash memory and 69K of RAM, and all the memory is protected with ECC, error correction code. And the smaller is also a TMS 320 F280037. It has about the same specs as this one, but obviously less I/O ports or smaller, less capabilities. Yeah, that's quite some CPU power for a power supply, yes. And yeah, that's the reason why even power supplies sometimes need a firmware update. It's not something that happens frequently, but from time to time. And there are some occasions where you have power supplies with different firmwares and they won't work together properly, so you first have to update them before you can install them. But now this is a brand new thing here, maybe 1 or 2 years old, maybe 1 year old. So you don't have to care about firmware updates yet. And yeah, I think that's about it. And yeah, I hope you enjoyed this little excursion into high power server power supplies and also the data center power grid details. Yeah, thanks for watching.